Good morning, everyone. Yes, I'm Olaf, and I guess my job today is to give you a bit of a reality check on metal additive manufacturing in particular, in terms of where it's at today. And I guess my key take-home message for today is that, in my opinion, design for additive manufacturing, it's not a luxury. It's not something you should do, it's something you must do. Otherwise, it becomes unfeasible to use additive manufacturing for much of production. So, it's an old process. I mean, additive manufacturing has been around for 30 years, close to 30 years today, and you wonder, is it suitable for production as it is today? In some cases, absolutely yes. In many cases, not quite yet today, whether it's for surface quality reasons, whether it's for metallurgical reasons, but the biggest one is for cost reasons. And you might be wondering why I'm showing pictures of sand casting down below. I think it's actually quite appropriate. In my opinion, additive manufacturing, metal additive manufacturing today is roughly comparable to sand casting. If you look at the surface quality of the parts coming out, you look at the metallurgical properties, in fact, you're slightly better than sand casting in most aspects. But if you think of it like you think of sand casting in terms of post-processing. So here, for example, we've got a picture of an engine block. If you sand cast the engine block, you're going to need to skim the heads, you're going to need to bore the pistons. Anywhere where you need an engineering quality fit or surface finish, you're going to need to do post-processing. Additive manufacturing, very much the same in that respect. Anywhere where you need a good engineering quality surface finish, you will need to do extra work. And in fact, this is from Formnext from last year. I think it's an Audi engine block printed in aluminium. And it's a very, very nice example of additive manufacturing. You see the back row of pistons is as it comes off the machine, the front row of pistons has been bored out. And you can immediately see the difference in surface finish. And you try to imagine what would happen if you ran pistons in the back row of cylinders. It would just grind itself apart. So I will talk a lot about post-processing and the cost and time it takes for post-processing. But maybe it's probably interesting to look at the trend of where additive manufacturing has been going over the last 20 or so years. The growth has been phenomenal, exponential growth year on year, and there's no sign of it really slowing down. But in my opinion, the bulk of that growth has been driven by a few high-end customers. Parts like aeronautical parts, where cost of parts is not that critical, medical parts, and so on. So it's very rare today where you can walk into a standard consumer product, SME, and see them using additive manufacturing beyond prototyping. So for manufacturing today, it's still in the realm of the very high-end, high-value companies. And you've got to wonder why. Why is it not being more broadly adopted by all companies? And to my mind, the simple reason is cost. Particularly with metal additive manufacturing. The cost is just phenomenally high, way too high for normal companies to adopt. And over the last few years, I've been wondering, what is it that drives the cost of both metal and also plastic additive manufacturing? A lot of it applies equally to both sides. So I've been looking a lot at what part of the AM process affects the cost the most, and the other question is, can we control that cost by designing for additive manufacturing? So my next couple of slides are really about that, about how you can try to redesign parts to make them more cost-effective to produce for metal additive manufacturing. So to my mind, there's various costs. Material costs, energy cost, labor cost. Labor cost typically 2 to 3%, not particularly high. The biggest single contributing factor to cost in most cases is machine time. So your average machine time, depending on the cost of the machine, typically you're talking around $65 an hour machine time. Now, that's fairly close to a high-end 5-axis CNC machine, roughly the same general operating cost. The difference is the time it takes to produce a part. A metal part, 10 hours, you're smiling. That's a good time. So at $65 an hour, that's $650. But with metal parts, typically 100 hours, very easy. 200 hours, even more. So 100 hours, you now jump up to $6,500. Now you start to wonder about, is there a way of reducing costs? So you wonder, if machine time is the biggest cost contributor, what is it that really causes that extreme high, cost? So here we have a very simple part. It's a block manifold. Basically, it's a block of material with a bunch of pipes drilled through it for hydraulic fluid to go through, for example. This is the way they've been manufactured, still mostly today. They drill a bunch of holes, they block some of them, and now you've got a series of connecting pipes to go through it. Now, if you draw a section through there, that's roughly what that section would look like, and that's the work the laser, I'm thinking powder bed fusion mostly now, the laser has to travel through hundreds of lines to draw that layer of the slice. So imagine it's like taking a piece of paper and a pencil, drawing a square and filling in the square. So drawing the square very quick, filling in the square hundreds and hundreds of lines. So in this case, let's say you've got a 0.1 mil hatch spacing. So the space between the lines is 0.1 of a mil. Typically, they can be a bit less, up to about 0.15, but 0.1 is a good number to work with because it makes the calculations easier. That means if that block is 10 centimeters by 10 centimeters, 100 millimeters square, you've got over 100 meters the laser has to travel. With a 100-watt laser, you're typically traveling at about 330 to 370, 400 millimeters per second. That means to do one layer, you're talking about 5 minutes. Or $5 worth of machine time at $65 an hour. So you think $5, it's a bargain, it's cheap. You've got to remember, if your layer thickness is 50 microns, you've got 2,000 layers. Now suddenly you can see where the cost starts to come up. So just to give you a bad design example, but to give you the alternative, if you take that block and you shell it out and just leave a 2 millimeter wall thickness, now you take a slice through it, and you can see the area the length the laser has to travel now gets reduced to about 4.5 meters. So over 95% less work the laser has to do to travel that space. So you drop down to about 25 cents per layer. Big saving, but not ideal. Your block will be filled with powder or support material, which is not ideal. So maybe a better approach is to redesign it for additive manufacturing. So for example, in this case, we take our block, we shell it out, and in about 5 seconds, we're left with the functional side of the manifold. And we can now say, we'll run this through the software that'll generate support material. We'll talk more about support material in a few minutes. But this is the 2 print orientations you could have. I suppose you could also put it at 45-degree angles. And that's the amount of support material to anchor the part down for heat transfer. Now, if weight reduction is the only objective, to make the manifold as light as possible, this would probably be an acceptable solution. And you would say, yes, I'll suffer through having to remove the support material afterwards. But if it's not just about weight saving, you might redesign it, for example, like that, with a few extra walls between the horizontal channels, so the walls replace the support material, and now you can see the only support material is down the bottom, comes out of the machine, chop it off the plate, and you're good to go. So this is what design for additive manufacturing means when I talk about it, is redesigning it to make it as fast and as low post-processing as possible to manufacture. So in the case of a manifold, if you look at the original solid block manifold, it's about 190 hours to print. Now think about one of your standard injection molding CNC machines being out of action for 190 hours doing one job. Think of the cost of that. You compare that to the cost, and these are real prices, real quotes. The quote for the solid block manifold in AM in stainless steel, $15,000 for a 10 centimeter by 10 centimeter by 10 centimeter block of steel. I mean, that is just robbery. Nobody can afford that. It's just too expensive. Comparison, still expensive. You're under $2,000 for the optimized one. You start to see, now you can start to see that design for AM, it's not a luxury. It's something you have to do in almost all cases. There are a few exceptions, but by and large, you must redesign for AM. So a real world example of that, another block manifold. This is one we did for Atlas Copco about 8-9 months ago. So again, same as before. This one's a bit bigger. It's 200 by 100 by 100. This is an hydraulic manifold that goes onto the end of one of their underground drilling rigs. We redesigned it for them, and we went from 14.6 kilos and dropped it down to 1.3 kilos. So 90% weight saving. Now this is on the end of an extendable boom. Now you can start to see that the weight difference is a huge benefit to be able to reduce the weight. The other big thing is functionality-wise. On the original manifold, the pipes went out in every direction, not because it's the best direction for pipes to come out of, but because that's the easiest direction to drill from. In the redesigned one, we had all the pipes coming in and out in line, which means it takes less space on the machine to be able, so you get more space for other things to go on. This is the manifold, again, minimum support material, and where there is support material, it's relatively easy to remove. And here it is, still in the machine with a powder on it, and finished in aluminium. So this was printed by Lasertech, still not polished up, bead blasted to make it look pretty, but this is now the finished product. And again, a 90% weight saving. I think the print time on this was 24, 28 hours or something like that. So still a long print time, but compared to printing the solid block, very, very reasonable. And I thought I'd give you one more example of design for you, and maybe to get you onto the fun side of additive manufacturing. This is a project I did about 4 or 5 months ago. It's a little desktop distillery for the executive who has too much time on his hands. So the idea is you put this on your desk, put a candle, put some wine on one side, and you get fortified wine coming out the other with some ice cubes on the cooling side. And you can see the size of it. It's about, the diameter of the barrels is about 50 millimeters. So it's a silly example, but again, when I designed this, this was designed for metal AM so that it's printed with, again, no support material. So simple strategies like between the spiral coil that goes up, I've put a wall between the coils to avoid having support material, because support material in there would be a nightmare to remove. And the same, the walls reinforcing, again, don't need any support material. So again, it comes out of the machine, cut it off the plate, and you're good to go with the part. So again, reinforcing that whole idea of design for additive manufacturing. So, I guess, to me, probably the 7 biggest design for additive manufacturing rules all put together in one slide. And the first one is probably the most important. The number 1 rule is it depends. And what I'm talking about here is people always ask, what's the smallest hole size I can make? What's the smallest slot? What's the thinnest wall I can make? And the answer, unfortunately, is it depends. Depends on the thickness, for example, will determine the size hole you can get through. The thicker your part becomes, the bigger the hole has to be before it becomes blocked. For example, so one of the problems with AM is the knowledge that is needed is maybe a little bit more sophisticated than, say, design for injection molding or casting or extrusion, because it takes a little bit of common sense or a little bit of a judgment call to apply that it depends rule. Number 2 rule is, should you be using additive in the first place? We have a lot of companies come to us and say, can you print this part? And we say, well, yes, but what's the point? It's going to cost you 3 times more, not be as good. Why do you want to print it? Very simple way to approach it. The other one is a bit stranger, but it doesn't cost anything more to make your product beautiful. With conventional manufacturing, particularly if you're CNC machining, every extra operation costs more money. If you want to fill it, if you want to round all the corners, that's more machining time, it costs more money. With additive, makes no difference. So why not put logos, part numbers, and so on in? Print orientation and support material. We'll talk a bit more about that later. But support material is sort of one of the nightmares of additive manufacturing. A lot of companies, Daimler, EOS, Premium, Aerotech, they say up to 70% of your part can be in post-processing. So you imagine our 100-hour part, which costs $6,500 to print. Let's be conservative and say you have 50% post-processing. You now jump your part up to $13,000. So again, designing to avoid that post-processing, very, very critical. Large masses of material. So that manifold was a perfect example of that. If you have a large mass of material, the laser has a lot more work to do, so it takes time. But also you have all sorts of residual stress in the part, which is generally speaking not a good thing. The residual stress is the reason why you need support material in the first place. It doesn't mean residual stress is always bad. Some of it is good, but you've got to control it in the right way. And again, fillet everything. Anytime you have a sharp corner, you're going to get stress concentrations. Again, not good. That's where the part will break, and it's another reason for needing support material. By introducing fillets everywhere, you can reduce that problem to a large extent. So as I said, there's many, many, many more rules of design for additive manufacturing, and literally books of guidelines for hole sizes, wall thicknesses, and so on. But as a thought process, I find these 7 sort of overall ways of thinking actually help a lot in terms of designing parts for additive manufacturing. So the last few slides are the opportunities. What can we do with additive manufacturing? When should we be using it? And of course, everybody knows the complexity for free, where geometrically complex parts are hugely advantageous to use additive manufacturing for, because they're either impossible to make using conventional or very expensive to make. And in that, I include conformal cooling channels, for example, that you couldn't make any other way. Part consolidation, where you take many simple parts, put them together into one much more complex part. Topology optimization, lattice structures, I think we're going to hear a lot about that today, to make lighter weight parts. Tool-free production, shorten lead time. But to my mind, again, all of these, to take advantage of them, you've got to design your parts. You cannot take a conventionally designed part and expect to get fantastic results with additive manufacturing. Again, both metal and plastic, but metal in particular. So some examples of that. This is one of my favorite, because it's luxury tapware, so it's art for your kitchen or your bathroom. So printed in steel, and again, you look at this bottom one here and you think, how does the water get from the top to the bottom? And that's because with additive manufacturing, you can print these twisting pipes that would be very hard or impossible to manufacture any other way. Beautiful examples of design for additive manufacturing and complexity for free. Just something to keep in mind, a set of these will cost you $12,000, so 120,000 crowns. So high value, low volume today. And my interest in design for additive manufacturing is trying to change that barrier, that limit, to being more, maybe not cheap disposable products, but certainly slightly less high value than these ones. Another example, this was one we did for Tetrapack last year. So it's actually quite a boring engineering part. It's an induction sealer to seal milk cartons. So it's a block of stainless steel, and in the top we've got a copper coil. You've got two of these together. You squeeze them together with a cardboard in between, put power through them, and you induce an electromagnetic current which heats up the cardboard and melts the polymer on the cardboard together. The little missing circle in the middle, that's where the plastic cap goes to avoid being hit by the sealers. Now, the way these work is the faster you can cool down the sealer after each seal, the faster you can run the machine. So today, the way they cool these, they drill, you can see the little red marks, they drill two vertical holes, drill a long horizontal hole, then they plug the right-hand end of it and create a channel through which they can send coolant to cool the sealer down. Now, as I said, the quicker you can run it, you can cool it down, the faster you can run the machine. So they came to us and said, we're interested in exploring additive manufacturing, but we want to know how it can add value to what we're doing. So we redesigned it for them. The first thing we did was we hollowed it out and put a lattice structure on the inside, which dropped the weight from 320 to 160 grams. So about a 50% weight saving, usually relatively easy to achieve. 40 to 60% is not hard. Now you think, so what? What does it mean if it's lighter? Well, if it's lighter, the motors in the machine don't have to work as hard. So everything becomes easier. But the big change was the cooling channel, which you can now see running all the way across, starts round. As it gets to the horizontal parts, it goes triangular, so you've got a much wider area of cooling going through. And you can cool it much quicker. Now, in this case, we were somewhat limited. We couldn't move the inlet and the outlet port outwards, which would have been nice to do because they had to fix to an existing machine. So again, there's always some compromise when you're designing a part that goes into an existing system. And that's it in 17.4 pH stainless steel there on the right there with a section cut through it. But here's the finite element analysis of it, and you can see on the left-hand side, the conventional design, there's a big hot spot in the middle where the milk carton is, which means that's going to take a lot longer to cool down, possibly even give you uneven sealing, because it's going to be hotter in that area. Whereas the one on the right, the redesigned one, we have a nice even heat distribution on the top. But where it gets more interesting, this is the temperature of the water coming out. And on the redesigned one, the water coming out is more than twice as hot as on the conventional one, which tells us it's removing twice as much heat than the conventional one. So now you can start to see where design for additive manufacturing can add real value, because now they can run the machine potentially twice as fast. That's still in the testing stages to see whether it really works as well as the analysis says it's going to work. But it is one of those areas of interest to keep pushing on. Next example, again, I think we'll hear much more about that today, topology optimization. So this is the idea of removing material that's not doing anything useful. So this is a little titanium bottle opener I have on my keychain. So it's a very boring object, but it's quite a nice demonstration of reducing the weight. So most products, if we look at this lectern, for example, if we do an analysis of it, an FEA analysis of it, we'll find probably 40 to 60% of the material from a structural point of view is doing nothing useful. So why not remove that material? And that's what topology optimization is about. It's doing an analysis on the product with the right loads and stresses and removing any unnecessary material that's not doing anything useful. So if we were going to make this the conventional way, we'd start with a block of, in this case, aluminium. It would weigh about 10 grams. We'd put it on a CNC machine, and we'd cut away the center part, and that would be the finished product. And in fact, you go to a lot of drink stores, and you can buy pretty much that exact bottle opener, usually extruded in aluminium, and it weighs about 4 grams. In contrast, the topology optimized one, under a gram, and rated for 300 kilos. Now, 90% weight saving, it's quite rare to achieve that much, but 40 to 60%, not all that hard to achieve. So as I said, a very, very growing area of additive manufacturing in general. And one more example, part consolidation. So this is an example from about 3 years ago now, but NASA did a rocket engine where they took 115 parts, brought them all together and printed the whole engine in 2 parts. Now from the outside, the 2 sort of copper-looking parts there, they're pretty boring on the outside. Believe me, on the inside, they're incredibly complex. You have twisted pipes leading the fuel where it needs to and so on, baffles to direct the energy the right way. Incredibly complex part. But again, think of it from a production point of view, going from 115 components down to 2. You don't need a room full of spare parts anymore. The assembly labor, the reliability, all of those factors that start to have an impact on how your product works, how easy it is to assemble, and the economics of it. So as I said, those are just some examples of additive manufacturing where they can truly add value. And to finish off on additive manufacturing, what I like to call the dirty little secret, the whole area of post-processing. Support material in particular. Now, post-processing is not just support material, but that's probably the biggest guilty party. So besides that, you've got heat treatment, hipping, and so on. But in this case, this is a little, again, I've got it on my keychain for those of you who want to see it afterwards. It's a little titanium spanner. We had a conference similar to this in New Zealand 5 years ago, 6 years ago now, and we gave every person, we printed 250 of these little spanners. So those blocks of material underneath, for those of you who are not familiar, is what we refer to as anchors or support material. Now, partly it is there to support, but mostly it's there for heat transfer, to suck the heat out of the part, to stop it from distorting. Because effectively with metal AM, we're welding. And with welding, if you don't get rid of the heat, everything distorts. So all of that has to be removed. Now, in some cases, with easy parts, you can CNC machine it off, wire cut it off, saw it off. In this case, we had student slave labor, so it wasn't too bad. We just had a team of students with Dremels breaking it off and trimming it down by hand. One more example, which is a little 3D printed aluminium guitar I did about, I don't know, 9 months ago, 10 months ago. So this is the guitar coming out of the machine still on the platform. It's still welded to the platform. And the design is barbed wire with flowers inside. You can still see all of the support material between the barbed wires. And we've got a close-up of it here. So all of that material in between the top and the bottom, and even under the flower petals, between the flower petals, has to be removed. And in this case, it's very complex geometry. The only way to remove it is by hand. So by the end of this, my hands were literally bleeding. This was the first part I had made where I removed the support material myself. In the past, I've had many, many metal parts made, but they always come to me already finished. And I wanted to experience, what's this all about? I know about support material, but what's it really like? So as Zylock, the company in Holland, printed it, sent me the 2 guitar bodies, and the finished product, if I may say so, is quite stunning. But you look at the numbers on it. The print time, not too bad. 9 hours of print time, all thin sections everywhere, quite quick to print. 30 hours, 33 hours of stress relief. 8 days of post-processing. 4 days to remove the support, 4 days to make it look nice. So to finish off, what's missing? And that, I think we're going to hear a lot more of that today. More materials, better surface finishes. We're currently on the right side. We probably want to be on the left side of that surface finish scales. Better design tools, optimized. And the big one to me is education in design for additive manufacturing in our basic engineering curriculum. It needs to be part of standard education. And I believe one of our speakers this morning will be talking about exactly that. So with that, I'll finish off and hand over to Elizabeth for if there's any questions from anybody or, yes.
First of all, thank you so much, Olaf, for this interesting speech.
Thank you.